Okay, so now we're recording. So welcome to the second lecture on Twistor theory. This class is going to be shorter than yesterday's. From the questions that were presented yesterday. There were a couple of people that also sent me emails with questions. And I thought we should probably review some of the stuff that I said, especially more towards the end, I guess, of the first class, because I'm probably that's usually stuff that should be covered in like a quantum field theory course, but it really depends on the kind of approach that you're taking. So it might not be obvious to anyone. So as thinking about this as being a school, we want you all to learn as much as possible. This is more for you guys than just for us who are teaching. So that's why we gotta adapt the course a little bit to make it more useful for the students. So I'm going to review some of the stuff yesterday. I encourage you to ask questions. I am going to give out some new stuff around today, and some of you might want to check out the website later. There's already a set of lecture notes. I already uploaded the lecture notes from yesterday over there, and there are some exercises, but I've already asked for from another organizer to update the part of the what would have been the lecture 2 lecture notes, which also have some exercises. So if we end up a little bit earlier than yesterday, just use this time to try to work through the exercise that try to build a little bit more of intuition, play around with indices, because these things, if this is the first time of you guys seeing them, you should probably spend some time really getting to grips with this kind of things. So let's do some review. Yesterday, of course, I'm not gonna review the whole lecture, but an important point. Probably I should have started with the complexification of Minkowski, because I think that probably is more a little bit easier to assimilate. So what we were doing at some point of yesterday's class was that we were complexifying Minkowski space-time, which just means that I was defining M as being as being R4 with a if the lecture notes, well, somebody sent here the chat, the lecture notes is a 404 error, because probably the other organizer is just uploading them. So wait until the end of the lecture to try to pick up those notes. Yeah. So yeah. So what I mean by Minkowski spacetime is essentially R4 with the Minkowski metric that gives that bilinear form that we all know and love. And what I mean by complexification is just that I'm moving to M sub index C, which is nothing but the R4 where the coordinates now have complex values. So we're effectively working in C4, and now we have some sort of some tensor. I'm writing epsilon. This is somewhat of that's not too much of a good notation, just because we define the Levi-Civita tensor as a two-dimensional a tensor that raises and lower indices associated to a two-dimensional complex space. But I just want to, I'm just writing this epsilon down because this is because we effectively are going to work in like this sort of two-dimensional subspaces of C2, which is each copy of the SL2C acts on. Well, because when we did this classification, what we did was we were taking some vector that we defined on R4, which had these Lorentz indices A. Let me write it a little bit better, and we were mapping them, by means of that by means of that transformation, which we take the components and multiply them by the Pauli matrices. So we were writing them as these two-dimensional objects, which depend on the Pauli matrices. And I'm not going to write the full matrix form because we're going to pretty much work with them today. I thought about doing some more explicit examples today, so you guys can get just these ideas. So, okay, now, so for now, I just up to this point, I just all that I did was I took the components of a four-dimensional real vector and I scrambled them around in some 2x2 matrix, and I claim that this represents the same thing in that you know there's more than just a transformation. There's more than a mathematical transformation between them. You know, it's physical, and the reason is, well, there's a group theoretical reason, which I think is the more elegant one, is that you can pretty much sum it down in this phrase, which is a vector on MC. So a vector in the complexification of Minkowski lives in the 1/2, 1/2 representation of SL2C cross SL2C. So, and the reason why this is true essentially boils down to, and those who have studied a little bit about Lie algebras will understand a little bit better what I'm saying. So the reason is that you have an isomorphism between the Lie algebras associated with these groups, which is little so 4, C. So this is isomorphic to 2 copies of the Lie algebra associated with SL2C. And if you remember, please provide the link to the site. So yeah, you guys were supposed to have the link to the website. It's the same website you did you registered for the school. So yeah, but I can send it by the end of the lecture, so I'll get too distracted. So as you remember, you know, if you think about these Lie groups as being manifolds, you know, you can think about the Lie algebras as describing the tangent space close to the identity of these groups. So these are essentially where the tangent vectors are going to be living. So if you're talking about vectors on MC from this point of view, you're thinking majorly as, you know, being this. Oh, it's okay. Thank you for providing the link. You're thinking about these vectors in terms of the Lie algebras associated with them. And the thing is that this isomorphism, this is an actual isomorphism for between the algebras, but they provide this implies that, you know, the groups themselves are isomorphic, at least locally. So this is a local isomorphism between SL2C cross SL2C. So this is essentially tells you that an element of what you can think about this in kind of like a crude manner is that if you have a vector, well, a vector in R3, you know, in 3-dimensional Euclidean space is something that you can rotate. You know, it's something that you can use SO3, you know, the group of special orthogonal transformation, you know, the group of rotations in 3 dimensions to rotate that vector. You know, the same way that a vector in Minkowski spacetime is something that you can rotate using the Lorentz group now, not just SO3. It's also 1,3. And the same thing is that a vector here in this C4 is something that you can rotate using this kind of group. But this group, you know, at least locally, and if you think about if you're thinking about tangent vectors, that's enough. It's locally isomorphic to 2 copies of the SL2C across SL2C. This means that you can decompose that the vector is in in representation theory terms tells you that a vector in SO4, C is not the fundamental representation. You know, it is reducible. You can reduce it to 2 copies, to 2 things in which the SO2C acts on. Okay, and this is why we can do this kind of transformation over here and still get the notion of a vector. This is why I'm always telling you that you can, when you complexify these things, you can just you can exchange a vector index by a pair of vial indices, spin order indices of opposite chirality, because you're just, you're just working in two copies of the SL2C. So I hope this clears a little bit about this. So if you're not at all familiar with what I just said, if all this sounds a lot sounds Greek or something, there's a very nice reference which it is more in the context of quantum mechanics and quantum field theory, but I think it's a great book, and its first couple of chapters are really well written and really good, which is Maggiori's book on QFT. So I think it's something called like quantum field theory, a modern approach, or something like that. But if I remember, it's chapter 2, which it talks about representation of the Lorentz group, and it talks really in depth and at a level that is very adequate for like the average theoretical physicist. There's also another book which is pretty much a classic, which is okay, I forget now. It's Lie algebras, Lie groups and Lie algebra for particle physics. I forget the Lie groups and Lie algebras for particle physicists. George I. Yeah. This is by George I. This is a little bit more extensive, and but it's also very good. Yeah, Raul just sent in the chat a modern introduction to quantum field theory. That's a great book. That would be my choice. But some people prefer George I. George I think it's also a great book. It's more extensive. Okay. So there was a question here. When you write VAs, are you using the A to represent specific component of the vector, or does VA denote the whole vector in the vector space V? That's a good question. So rigorously, that will just represent like a component, like the components of the you would use this as like an abstract index notation, in which that thing just represent the component. But often physicists are kind of lax with this kind of notation. They call the whole the thing with the index, they call it the vector, because we're usually interested in the transformation properties of the components of the vector, and that's enough, because we want to, in general, to work in like a coordinate independent manner. Sorry, in a basis in a coordinate independent manner. So it doesn't really matter the choice of basis that you have, because the components of the vector there, if you really want to write down the vector, you need like some sort of basis. But you want to write your things in the most covariant way possible, and you want these things only in terms of the components, because then you don't need to choose yourself a basis. So when you write this thing down with the indices, what philosophically you're trying to say is that, okay, you're not really caring about the coordinate system, any coordinate system, any one, it's fine. If I pick one, if you pick the other, you should pretty much get the same result. That's the main lesson of general relativity. So yeah, but yeah, that is a good question. But and it really is gonna depend on the reference you're using. So here I'm usually calling the components, the vector with the indices, I'm calling them vectors. But because that's mostly the physicist notation. Yeah, thanks. Okay, so that being said, okay, this review being said, yeah, definitely check out these books if you're not at all familiar with this with at least this. So we now move a little bit to what I wanted to talk about. So yeah, what we did. Okay, so just a tiny little bit more review of yesterday. What we did was, okay, so we were working in C4, which we were understanding as kind of complexification of Minkowski spacetime, and then we just imposed this coordinates, this equivalence relation of the coordinates, which makes us now moving to what is called the projected 3 plane. So we picked some, we coordinatized this like Hassan's question, I'm using the vector with the index. I'm just representing the components. So each component scales in this way, where R is different from 0 as a complex parameter. So this is CP3. And when I do this, I can also, choose these coordinates to be of a specific form. And what I chose was mu alpha dot and lambda alpha. And, if I just think about C4, and this is just a choice of coordinates that I can make the way to, write each point of this complex 4 space. And I was interested in choosing a subset of this CP3, which I was denoting by PT. And which subset is this exactly? Is a subset that I get when I type down these two coordinates in this way. So I have me alpha prime alpha dot, sorry, is equal to x alpha dot lambda alpha. So I'm just picking. I am picking a plane inside this thing. When I do this thing together with this, with this scaling of the coordinates, what I get is a CP1, which I denote x, which of course is a subset in this thing. So the lines which describe and all these are inside this Twistor space. So all the lines inside this Twistor space are basically Riemann spheres. There are CP1s that are inside. Okay, and what we saw last class was that you can, when you complexify the space, the Minkowski space, often you want to recover, either Minkowski in Lorentz signature. We also saw that we could recover Euclidean space, four-dimensional Euclidean space. There's an exercise in the lecture notes that you're supposed to get something that is called the split signature space, which is something that the metric has two minus signs and two plus signs. So yeah, you can take a look at these at the end of the lecture. So I want to today I want to continue a little bit on this discussion about reality structures. So this new section is going to be called Twistor geometry. I will start with this today, and I will and tomorrow. I will talk about conformal, what are called complex structures and conformal structures that you can put on this, and then I'll see what else there's time to talk a little bit about, because I want to get a little bit into applications by the last lecture. So in this thing, let's talk a little bit about these reality structures again. So what we did, and let's be very slow with this part, because I know it can get confusing. I certainly had some hard time when I was first learning about this stuff. So let's take it easy. So we saw that we could pick some different notions of conjugation. Of conjugation. So what I mean by this? So what we had, the structure that we were using to coordinatize C4 were four complex numbers which we can arrange in a matrix, which is convenient to do so, because it easily allows us to see the spinorial structure and kind of relate this with actual space-time. So we had these four complex numbers. So each one of these axes is a complex number. And we saw that if we endow, if we try to coordinate C4 or even Twistor space with this with this kind of structure, if we try to relate them with this kind of things, we can recover. I showed you to you guys the Lorentzian signature Minkowski spacetime if you impose the reality conditions in which this x alpha dot is equal to the transpose conjugate of this guy. So you pretty much take this matrix. You take the complex conjugate of this guy, the usual notion that we have, and then you take the transpose, and then you enforce that these things need to be the same. Then you get this is a choice of reality structure. In the same way that we had the Euclidean signature, in which we had, in which we had, we imposed that this guy had to be equal to another conjugation that we took that was kind of a funny one, which had this kind of quaternionic nature. So let's see what else happens once we impose these reality conditions on Twistor space. What are the consequences? So if we now the Lorentzian, so let me be explicit here, and let me write so let's take the conjugate of this guy. So this is the Lorentzian signature conjugation, if you will, which you just take the other one, you take the complex conjugation. So you should get so you should flip signs here. Well, not this part here. These guys here remain the same, but you just take the complex conjugate of each one of them. But then the two guys in the off diagonal elements, they exchange with each other. So you get x bar 1 minus x bar 2. This comes from the fact that I just exchange this first element here with this guy, and then I change the sign of the i's, and then you have x bar 1 plus I x bar 2 over here. Okay, so I did this. So I just so all I did was take the complex conjugate and the transpose. So if I pick the coordinates, so the way that I was coordinatizing the Twistor space, which was in terms of the ZAs, which are mu alpha dot lambda alpha. So this conjugation, let me call it the Lorentzian conjugation. Defines a conjugate for these coordinates, which is basically z bar of a equals, I define it as lambda bar alpha dot mu bar alpha. And you see, I exchanged both spinors in their place in the vector, and I also changed, which is something important. I changed the order of the indices over here. A way you can understand this is that I'm writing everything as being like row vectors. I'm not differentiating between the column vectors and row vectors. And when I take the transpose, what I'm essentially doing is that I'm changing in between the representation of the SL2C cross SL2C. So I need to make this change of the indices. This is you can think about this in terms of matrix terms, because that's exactly what is going on. So when I define this, this conjugation, what it does. So this flips the representations, the reps. So because of this flipping thing, we are led to consider if these guys are coordinatizing with PT, the Twistor space, we are led to consider a dual space which sometimes is denoted PT with a little v on top. And this space is just the same, which is just the same as PT, but with coordinates. So now I need to define a new set of coordinates, which I'm going to do by writing them with a lower index, kind of like in the same way that you have like a vector space in the dual space, which, you know, for those who are, you know, remember their course in general relativity, you know, you just have the thing that have index up and index down, and, you know, one of them transforms like a vector, the other one transforms like a in an inverse way, and then when you contract one with the other, you get a scalar. You know, one forms something that sends a vector to a number. So I write this with an index down because I'm talking about a dual space. I'm talking about a space of linear functionals. So, and this guy, I'm going to coordinatize it. I'm going to put a tilde, which is suggestive, but I want to make it clear that I'm not making this the complex conjugate yet. So what it will turn out is that when I take the Lorentzian conjugation, I'm just changing between the Twistor space and the dual Twistor space, or at least a subset of the dual Twistor space. So this is the guy that I'm coordinatizing with the coordinates in the exchanging in the exchange in exchanging the representations, you know, flipping you know, just raising and lowering the indices. So naturally, you know, we have an inner product between these guys. Somebody sent a message that just said basis. I'm not really sure what yeah, basis is a word, definitely. So you can, you know, if you do this, you have a natural inner product, which is just given by, you know, if you take z dot w, which is just in terms of the components, as somebody was asking, it's just this. And then if you do this carefully, you know, you just contract the correct indices, you should get mu lambda tilde plus mu tilde lambda using those SO2C invariant inner products that I showed you guys in the last lecture. So just contracting alpha dots with alpha dots and alphas with alphas. Okay. So if you do, so naturally we can explore this to, you know, write down this in terms of, you know, the inner product of the z with its complex conjugate, and this is, of course, it's just, you know, mu lambda bar plus mu bar lambda, where I just, you know, all I did was, you know, change the tildes for the bars. So what I'm effectively doing when I define this dual space, I declare that, you know, the complex conjugates of those coordinates are the subset of this PT of these, such that, you know, you have this kind of relationship over here. So this is kind of the formal way of defining these things. And why am I worrying about this? About this inner product, because this will give us some more information, even more information about what did these points in Twistor space corresponds in Minkowski space time. This is what we want to do all the time. Sorry, my tablet's a little bit messy today. Okay, so okay, let me see what I want to. Okay, I want to keep this thing, so let me copy. So, okay, I had this kind of things. So we can let us explore a little bit what happens when you consider the incidence relations that we saw last class. I'm going to modify them a little bit. I'm going to include a factor of I, and doesn't change anything. It's just, you know, it makes it a little bit easier for computations. So Now I'm writing the incidence relations. Let me put a modified because I'm just including factor of I. So if you compare your notes with the last lecture, you might be a little bit confused. But this doesn't, again, this doesn't change anything. It just makes computation a little bit easier. So I'm just writing mu this I x alpha dot lambda alpha, and the same thing for the dual space, which is just minus I x alpha dot lambda tilde alpha dot. I see there's a question in the chat. In the natural inner product, do we add the two or do we multiply? You are multiplying the components that are in the same representation. You're multiplying the alphas with alphas, the indices alpha on top and alpha down, and summing them with alpha dot on top and alpha dot on down. Yeah, that's how you do the actual computation of this. So, okay, so we have this modified incidence relations. So if we compute now, if we consider this, and this is a good exercise here, so you see that you're getting used with these inner products. So what you do is that you can show explicitly by this kind of computation, considering this tilde as being bars, that this is just equal to I x minus x dagger alpha dot lambda alpha lambda bar alpha dot. Now you might be a little bit surprised about this x dagger, but just remember that when we're taking the complex conjugation, this guy here becomes a dagger. So this is the only challenging part of the problem, and I just ruined it for you guys. But it's just you're just thinking about in terms of the dual space. You're thinking about that the subset of the dual space that the coordinates are related with the dagger, with the Hermitian of the X matrix. So if you do this computation, you find this, but if we want the Minkowski slice, we had to impose the condition that X is equal to X dagger. And let me put the indices here to be a little bit more explicit. Alpha and alpha dot. Sorry, this got a little bit messy. So what does it say to us? That this guy has to be 0 in order for you to obtain Minkowski spacetime if you impose this reality condition. Now that's interesting. That means that this reality, the reality condition, this reality condition over here of this equality, you had to impose it to say, okay, this x that is relating these coordinates, this parts of the coordinates in CP3, they are related to a point in space time when this condition holds, when this reality condition holds. Now, if this condition holds, it means that if you imply this conjugation, if you define this, if you induce this complex conjugation on the Twistor space, then the inner product between the point it is conjugated must be 0. So the set of points, this says that we can see the set of points of some line in Twistor space that correspond to Minkowski, so that we can see the set of points of S that corresponds to Minkowski. as the set, which I will denote as Pn, which is just the points of Pt, such that z dot z bar is equal to 0. There was a question. Is it from CP space and the W is from P space or both from same space? I guess you meant that Z is from CP3. Yes, it is from CP3. We're working the subset of CP3. We're not working the full thing. We're working the Twistor space. And the W is from, you can think about it as being the dual space. But as you probably remember from either linear algebra from general relativity, you can pretty much write it down the isomorphism between the space and the dual and its dual by means of the metric. So the metric that raises and lower indices is responsible by defining a isomorphism between these spaces. So they're pretty much the same. I think every space of linear functionals defines a vector space itself. So yeah, so that's the thing. So okay, this is cool. This is a subset of the Twistor space, which is called the space of null twistors. So the Minkowski, so the actual Twistor space of Minkowski space when we pick the Lorentz signature is the slice is a subset of PT where this relation holds. So what we had up to now is that we complexified. We started by complexifying, R4, or you can think about, complexifying Minkowski, and we got something more general, and we could pick, if we could pick, different reality conditions inside of it, but we were interested in thinking about these C4. We defined the projective space. We were interested in a subset of this projective space, and inside of there we could impose the reality conditions, and each reality condition will return the space time. So PT is is a subset of CP3, and then the actual Twistor space of Minkowski that returns the Lorentzian Minkowski spacetime, the R4 with the Lorentzian metric, all the thing that you could do special relativity on, is the subset of the Twistor space in which you have no twistors. So which are these twistors that obey this condition. So this again already kind of because we have no twistors involved. We saw last class that we also had no vectors involved. You can already see that there's like this flavor of like a corresponding between conformal structures. Because if you have light cones in your space time, you need transformation. If you want transformation that preserve the light cones, you're interested in transformation that preserve the angles, the 45-degree angles that define your light cones. So it is interesting to look at these things from a conformal structure standpoint, and this is what we're going to do on the next class. So while I take a sip of water, are there any questions about this? Okay, cool. So we can do again. We can ask the converse question. Okay, so we have if we define this the space of no twistors to correspond to points in space time. So if we take so a point of a space time is corresponding to the space of no twistors. Now what is a point in this space of no twistors corresponds to? So the question is, given a point in Pn, what is the corresponding structure on I see there's another question. Just to understand, this tells us that if we want to make sure that we only work with twistors that correspond to point space-time, we just have to make sure that there are no. Yes, the twistors, yes. So I guess your question is, what twistors are, if given the space of, the subspace of CP3, which is PT, which I call it the space of twistors. Which of these twistors do we need to think about the full PT subset, or do we only need to think about a subset of it? What I'm telling you is that yes, you only need to take a subset of it, which is the space of no twistors. Yes, to recover Minkowski space-time. If you want to recover, if you want to complexify and then go to like a Euclidean signature, because you want to do calculation, or if you want to go to split signature or something else, then you have to pick another subset. But yeah, you're absolutely right. Yes, good. More questions? Okay, so now given this point, so again, this relationship, this twistor correspondence is pretty much non-local. It's not like a point is going to a point here and over there. So we already saw that we could get from a point to like a line in twistor space. Now we're getting to this subset of these lines which the points along this line have this this relationship. So it's not very straightforward. It's valid to ask those questions. A point here is something here, and a point here is something else here. And what happens is that we saw that that the points what we had in the last class. Let me just remember what was the notation that I used, just not to make this confusing. Yeah, I think I did. Yeah, I think I did something. Yeah, what I did, what I wrote down is that we had these planes in that no, this is a little bit. This is not very confusing. This is a bit confusing. Yeah, I'm gonna have to rewrite a little bit this section of the notes before. I'll have to update the notes later. But the point is that we had, when we were not very satisfied with this. Okay, give me a second. Just let me just go back in the notes here and see how exactly I present this, so I won't confuse you. Hopefully. Okay. 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 Good. 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 Okay. So what I wrote down that we had this relationship, of the difference between two points in the space-time, in space-time. We had that this had to correspond to some sort of plane in the interstellar space, which I wrote down something like this. And I made the argument that when you contract the indices, you have like a leftover alpha dot index, which you can do pretty much write in terms of another spinner, which is arbitrary. And then the choice of the variation of the choice, they have this the spinner defines like it defines a plane. So we had this corresponding between no separated points in Minkowski space-time, and these alpha planes, this alpha planes on this on Twistor space. And the thing is that if we impose this this no condition, we determine, we single out one of these planes. We single out the plane in which lambda tilde is actually lambda bar, is the actual complex conjugate of this other guy. So what this means that a point z in Pn corresponds to a new no geodesic. And why does it define a question? Why does it define a plane and not a ring? I'm not sure what you're calling a ring. I'm not sure if you're thinking of mathematician's definition of a ring, or if you're actually thinking like a ring of spire. Well, it defines a plane because, well, you have like you have a product of two vectors, like it's like an external product of the two vectors, and that these kind of things, they define a plane. If one of them, if you fix one of them and you vary the other when you're taking the product, the thing that define a like a plane in this thing. Yeah, not really sure if that was a question, but anyway. Oh, think about spheres. Okay, no, it's fine. It's fine. Yeah, these things are kind of hard to visualize, like I said. But yeah. So it corresponds to this no geodesics. So yeah. I think this part got a little bit more confusing. I will I'm moving on to now. The point that I want to make is not well. It's not too important to get bogged in the details right now. It's just that I still want to explore this non-locality of this relationship between the twistor space and the space time. So the point is that you have this correspondence in the space of twistors, which is these this subset in which this relationship is made precise. Then when you do the other way around, you get no geodesics in space time. And now the filling the details is something that I'm gonna let you guys take a look at the notes later and take it on your own time. That's just I'm afraid I'm making things a little bit more confusing than they need to be. But yeah, so okay, so this was Lorenz's signature. So we picked up the what you will call the Minkowski spacetime with Lorenz's signature. So now I want to do the same for Euclidean. So for Euclidean, so what was the conjugation that we had in Euclidean for Euclidean? So we had that. Okay, let me just write the conjugate that we had. It was something like this. So we exchange the signs in here. So it's minus x bar 1 minus I x bar 2 minus x bar 1 plus I x bar 2 x bar 0 plus x bar 3. So this was the conjugation. Like I said, this is an example of something that is called like a quaternionic conjugation, because you have essentially to apply this conjugation 4 times before you go back to the thing. But it also defines something that is called an evolution in the on the other points of the twistor space. Now, again, I from some of the questions that I saw in the last lecture, some of you guys have some more refined mathematical training, and you might be a little bit confused because an evolution is something that also anti-commutes when you take the product, something that you define on an algebra. But again, I'm just borrowing the words that are used in the literature, and the common terminology here. And sometimes there are special cases of these more mathematical structures. Sometimes I'm just using the same name to represent something that is a little bit more general. So Try to stick with the definition that I'm using here and not trying to, at least for now, don't try to keep it related with stuff that you probably already know, because that's otherwise it can lead to some confusion, at least for now. At least for now. So when we do this conjugation on Euclidean, this induces a conjugation of the spinors, which goes something like this. So if I write down this alpha dot, and if I write that down pretty explicitly as two complex numbers A and B, so the complex conjugation will take me to a hat here, alpha dot equals to minus B bar A bar. You can pretty much you can work this out yourself, try to convince yourself from seeing how this hat conjugation here changes this matrix, the X matrix, and you pretty much see that you end up with this guy. Now, what is important is to see that we haven't raised or lowered the representations or change in between representations. So this induces this, and on the lambda alpha, which I'm going to write as CD. This induces also a lambda hat alpha, which is minus D bar C bar. Okay, I ran out of space. Let me just copy all of this and move to the next page so we can continue. This is the good part of using tablets to work on it, like an actual blackboard. Oops. Oh no, this is not what I wanted. Let me try this again. Oh. Oh no. Okay. Guess I pressed the wrong button. Okay. Now it should work. Yes. Good. Okay. So we had this in the this conjugation acting this way on the spinors. So this means that if we go on now to the considered coordinates on the PT coordinates, which are the ZAs, so which I wrote down as mu alpha dot lambda alpha. So this complex conjugate is going to take me to a Z hat A, which is just given, and then you can work this out yourself. It's not difficult to see that this is just alpha dot with lambda alpha with a hat. Now, because we didn't change the in between the representation. We didn't raise and lower indices when we take this conjugation. We just change the actual components of this guys over here. So at the left of these components, this becomes a little bit more important. Now, if you want to, now you can do this exercise that that on Twistor space. So the hat defines an involution, meaning a map sigma from PT to PT, such that when you take twice the thing, you get minus the identity. So an exercise that you can do is to show that if you take Z two hats of A, this is just minus ZA. If you apply this twice, and the way to see this is you write down, you open up this these coordinates in terms of these A, B, C, and D, and you work out explicitly. If you take the conjugation, you flip both of them and you change the sign of the first entry, and then you flip again. You have to flip it again, taking a conjugate, which just returns to the complex numbers you had. But now both of them carry a minus sign, and this this minus sign comes out. So this is what happens in the Twistor space. It acts in this way. So and it turns out that if you do, because of this, This means that there are no points because this thing is an evolution. There are no points in PT which are invariant under sigma 2, which sigma 2, under sigma, which just means that I'm just because I applied them twice and get a minus sign. I don't have any points in this space that are invariant under this, and this is just a statement, because we cannot get the same thing. We don't have this kind. Well, in the Lorenzia case, we had points that were invariant under this conjugation, and we saw that these things are related to real no geodesics in Minkowski spacetime. This thing, it turns out that it's just a statement. There are no real no geodesics in Euclidean spacetime. Euclidean space. And this is kind of this is kind of obvious, right? Because we equip Euclidean space with a positive definite metric. So there is no causal structure that you could define using a positive definite metric. The whole gist of working with Minkowski is that inner product that I presented, the first thing that I presented to you guys is that thing is not positive definite. So you can use that thing to classify vectors between being time-like, space-like, and null. And that doesn't happen in Euclidean spacetime because it's positive definite. So you kind of recover this idea when you're working in Twistor space. And the statement just comes the positive definiteness of the metrics is expressed in this as the statement that there are no points in this Twistor space that are invariant under this evolution, under this transformation, which just means taking this complex conjugation. All right. Okay. And I'm just gonna say this one more thing, and then we can I think we can wrap it up for today, and then you guys will have some exercise that you can have a little bit of fun with, and think of more questions. So, okay, there are no points that are there are no points that are invariant under this, but there are things that are invariant, which are lines. So it turns out that lines are preserved under sigma. And how do we see this? So there's a construction, and which is something called a bi-twistor. So a bi-twistor is something that carries these two indices, and I write them as two coordinates, ZA and Z2B, in which I take the antisymmetric product between these guys. So this is just something like there's usually a normalization factor here. So I just want Z1A, ZB2 minus Z1B, Z2B, Z2A. Recall that notice that the antisymmetry is on the upper indices, not on the lower. So if I define this this kind of guy, we can you can write this, and this is an exercise. It's a fun exercise actually, to write this guy as in terms of using the incidence relations in terms of the coordinates. So this is what will be written something like this: dot beta dot is2 x alpha dot beta minus x beta dot alpha epsilon alpha beta. So you can write this bi-twistor over here, and the thing is that you can write this when Z1 and Z2 are on the same line. Because then your incidence relation only depends on X. It doesn't depend on X and a Y, meaning that this is just, I'm just saying that, mu alpha dot is equal to 1 alpha dot. This is X alpha dot lambda 1 alpha. And also that mu, let me put it back, beta 2 is equal to X beta dot, and 2 beta. So this is just a statement. If you have these two incidence relations, you can write this by Twistor in this form. So this is an exercise you should do. And the thing is that, well, again, appealing to just for the sake of having a little bit of intuition behind these things. If you have like a real plane, if you have 2 points on a plane, there's exactly, that we know known this since Euclid, that between two points there's only one line that passes through these 2 points. So the thing is that I'm saying that I'm claiming that if I have these 2 points in Twistor space, there's exactly one line that passes through them. And again, as the question in the beginning, we're saying you shouldn't take this analogy too literally, because this is not a line. This is a complex projective space. It's a Riemann sphere, so it's more complicated than that. But this is the kind of idea you should have. You can make these things a little bit more precise. But the thing is that is this. So what I'm saying is that if I write down this, I can this thing over here defines a line. It represents a line in Twistor space. And then, okay, since this guy, you can write a line in this way. You can coordinatize it in terms of a bi-twistor. This means we can try to see what happens if you apply this hat conjugation. So the claim is that XAB is equal to X hat EB, and this is also an exercise. This is easier. If you got too bogged in the details of this first exercise over here, you could just assume that this form is true, and then you could just go back to this thing. Okay, let me see what else. Okay, so there was a question. What are these lines representing Euclidean space? The lines. Oh, well, that's actually a good question. I'm not sure. I'm not sure of the answer. I will think about. I will think about. I will think about it. I didn't think about this, but yeah, your question. I understand your question, and it's valid, but I do not know the answer. Yeah. Which is, now thinking about in hindsight, it's kind of obvious. I think it's not too well. If my intuition is correct, it has to do with some vibration structure in Euclidean space. But that will be the first thing that I will answer tomorrow. I'm not 100% confident on my intuition right now. But okay, so if once you show this, you can show that these lines are invariant under this conjugation. So if okay, yeah. Okay. Yeah. I see. Yeah. Some of you people are sending me the questions like the private chat, and Yeah, you should make them public. I didn't notice that. Okay. So, all right. So make it okay. If you show that this is correct, you know, if you imposing the Euclidean imposing Euclidean reality conditions, you know, the yeah, reality condition. This implies that every point, when you have a point PT, you can associate it to R. So it's associated to a point in Euclidean space. Now I'm gonna be a little bit loose and just write it R4, but you understand this as being Euclidean. If you know if this reality condition if this invariance holds. So I guess this kind of answers the question that was asked about what are the lines, what do these lines correspond to in Euclidean space. So I think there's more to this than that, but the thing is that, well, we can associate these points once we consider the lines which are given by ZA, ZB, because these turn out to be the lines in which this condition hold. So, kind of answering what was their name, Hare Krishna's questions about what do these lines represent in Euclidean space. Again, I think I think there's a little bit more to that to this, but these lines, you know, the specific lines which have this form, which are constructed by, you know, Twistor and its hat conjugate, they correspond to a point in Euclidean space. So yeah, so a line in this space with this reality condition corresponds to a point now in Euclidean space. So yeah, okay. I think I'm gonna stop it for now, and I'll take some questions. I think I'm gonna stop the recording. I'm sorry it got a little bit messy more towards the end, but I think I'm gonna stop it now and, you know, let you guys work on the exercise and try to read a little bit the lecture notes, and I apologize a little bit for the confusion. But then tomorrow we will continue on. I will review some of the stuff. Of course, I'll try to take a little bit less time, and then we will move on to the talking about a little bit about complex structures and conformal structures. And hopefully tomorrow I can already show to you guys the Penrose transform, which is probably the main construction on Twistor space, and is one of the most beautiful constructed that we have in Twistor theory, and it's pretty useful for, you know, for people who are that have a more mathematical interest, but also people that are working because of want to learn this kind of things because of scattering amplitudes. So let me stop the recording, and I'll open up for questions so you guys won't feel too shy. Yeah, thank you. So.